Okay, so welcome back. In this module, let us have a look at how to model a digital logic called as tri-state buffer. In digital electronics, tri-state buffer is a very useful circuit element, and we are going to see how it is written, a code is written in Verilog for a tri-state one. But before that, let us have a look at what the tri-state buffer is and its basic principle, because after understanding how it works, you are better able to write the code for it. Okay, and we have, previous to this model, we have written a code for the inverter, and we have written a code, Verilog code, for a buffer. But this time we are going to write a code for the tri-state buffer. So here you see that it's a symbol for the inverter circuit. So you got the input A and the output Y is the complement of your input. Okay. Here is the symbol for the buffer circuit. So this is a simple buffer circuit. This is an inverter circuit. Okay. And here you got the input and the output is simply the input. So you see there is a difference here between CMOS, between an inverter and the buffer. Y is equal to complement of A, and here Y is simply the input A. But now look at this symbol. This is called as tri-state buffer. It has got three pins: enable, input pin, and the output pin. So in the form of a truth table, you can write enable pin, then you got the input pin, then you got the output pin, and your enable pin can be 0 or 1. And based on that, your output and inputs values can be written. So let us say when enable pin is 0, and in that case, when your input is 0 or 1, it doesn't matter. Output is high Z, which stands for high impedance state. However, when the enable pin is 1, as shown right here, when your input is 0, output is 0. When your input is 1, output is 1. So output in this case simply follows an input when you have enable pin set equal to 1. So this is how, otherwise it is in the high impedance state. So this is how the tri-state buffer works. Okay, so I hope you got the basic understanding clear. Once you have this understanding clear, it is very easy to write the code for the tri-state buffer. So there are two types of modeling, or two styles we can use. Data flow is the one, and second is the structural level or gate level. So gate level is the very lowest level of modeling style, where you specify what exactly, the way exactly you want your logic to be implemented. Okay, so let us have a focus on the data flow. As in the previous modules, we start with the using keyword module, then we give a name to our circuit. I have given name buffer underscore tri. Okay, that's my name. You can give any name, and then in the parentheses I can use outputs and inputs. So in my buffer, have a look at this symbol right over here. I have got two input pins, enable and in, and one single output. So I will say output Y here. So instead of out, I have written Y. So here it is Y. Instead of input, I have taken A. So here is my input. And third pin is enable. So En, instead of En, I have written enable. I can also write these pins like En, out, and in, but accordingly you have to choose. When bracket close, and then don't forget to add this semicolon. Then I have the output explicitly specified. I am saying Y is my output. Here I want to add some little bit information for you. You can also say output wire. Y. So you are basically specifying the output wire. So this is another practice of specifying which one is your output wire and which one are your input wire. But even if you don't do that, if you say like that output Y, then semicolon, that the synthesis tool will know, okay, this is your output wire. Otherwise, you specify explicitly that output wire is Y. Then my input, I have got two inputs, A and the enable, and then I end it with the semicolon. Here also, you can write input wire A and then input wire enable. Or instead, you would simply write input wire A, comma, enable. With this, the tool knows that you are specifying the A and enable are your wires, and those are input wires. Okay, so that's another practice. And once you do that, let me show you that. Then you use the assign keyword. Now here is a very interesting symbol. You say the assign keyword, then Y is your output, and then in bracket you write the enable. So this is the conditional operator you have to specify, that is a question mark. It says that when the enable pin is set to 1, your output is connected to the input, or input A is assigned to output Y. If enable pin is equal to 0, your output goes to high impedance state, which is given by this command or this syntax. One, there is a explanatory sign BZ. So this specify high Z state. Okay. So again, I repeat, this is a conditional operator question mark, which says if enable pin is 1, output gets connected to the input, or say input gets transferred to the output. If it is set to 0, enable pin is set to 0, your output goes to high Z state, that is indicated by this 1 dash BZ. And then you have this semicolon, obviously. And finally, you end the module. So that's it. So this is how you specify how your uh, how your code for the data flow modeling can be used. Okay, so let me clear this. Now let us have a focus on the gate level modeling. So gate level modeling that we can see right over. This is the code. Tri-state gate level modeling. Obviously, you start with the module, give a name to your model, buffer underscore try. In my case, in brackets, I will define all my inputs and output variables. So output is my Y is my output variable, A and enable are my input variables. And then I say output is Y. I can write in between wires. Explicitly, I can say that, oh, this is my output wire. And here also I can write wire and input wires, input A, comma, enable. So those are my input variables. That's my output variable. But now look at the difference. I am using a primitive in Verilog called as buff if 1. So you see buff if 1. That means I am implementing the tri-state buffer by instantiation of this primitive called buff if 1. I am using this primitive explicitly, and in bracket I am writing my output variable first, followed by input variables. You cannot have input variable first and then the output variable. No, this has to be satisfied. Output variable precedes the input variable. Now, how this command works? It says if the enable pin is equal to 1, output is assigned the value of input. If enable pin is assigned or is set to logic 0, output is otherwise in the high impedance state, which is basically this truth table. So that's how the Verilog will work. And finally, you have this end module. Okay, so these are the two modeling styles. There is one more modeling style called as behavioral modeling, which is our subject of next module. We will cover that. So hope you found this module useful. If you did so, share it with others for wider reach, and at the end of each videos from now onwards, you have option of clicking the thanks button on our videos. So if you have like that, you can choose to have it, and share your appreciation and the love for our modeling styles and the engaging content we will keep producing. Okay, so we wish you a happy learning. Stay tuned for more engaging content like this.